Hello, my name is Malcolm Griffiths. I've worked for over 40 years in the nuclear industry, and much of that time I've spent studying the effects of radiation on materials. And today I'd like to share with you some of the things I've learned about strain localization and fracture of nuclear reactor core materials. By way of introduction, I should say that the first time I got interested in this subject, if you can call it the subject, was back here around about 2008, 2009, working for Atomic Energy Canada Limited. I was program manager for the Fuel Channel Working Group, and we had a problem. There were some components in the CANDU reactor which were Inconel spacers, Inconel X750, and some tests were showing that they were degrading at a rate which was unusual, that people were not expecting. From my perspective, I'd been exposed to materials degradation enough to know that there was a problem, and that problem was probably related to helium embrittlement. However, many of my colleagues and certainly the engineering groups believed that there was another explanation for the degradation, and when an assessment document was written, it was written in terms of the failure mechanism for these components being the interaction of slip bands with grain boundaries. And that was kind of like a catch-all, hand-waving explanation for which there was no evidence. But at the same time, people like me were saying to everybody else, saying, well, you know, if you calculate how much helium is in this material, it's 20,000 atomic parts per million. At that time, we're now up to about 30,000 atomic parts per million, and the material are still degrading and failing in a very brittle manner. So it behooved me at that time to look into it. I mean, when people were saying I was responsible for understanding the effects of materials, and a lot of people were citing this magical thing called strain localization, which I deduced was stroke cracking, which I'll talk to you about, and it. Although I didn't know anything about it, I thought, well, I'd better find out about it and see if there's any basis for what they're saying. And that basically set me off on picking up as much information as I could about the mechanisms of strain localization. And it applies to zirconium alloys, austenitic alloys in particular, stainless steels, and nickel alloys. So I'll be talking interchangeably about all three types of materials. Zirconium alloys, of course, being hexagonal close packed, and the austenitic alloys being face-centered cubic primarily. So let's start with just some basics, because it'll be relevant for the remainder of the talk. So I just want to introduce a few general deformation mechanisms that apply to materials, whether it's irradiated or unirradiated, just so that we understand one another, and that when I am talking about different mechanisms, you at least are aware of where I'm coming from. So there are two main deformation mechanisms that I'm going to be covering. As one is cleavage fracture and ductile fracture, although the cleavage fracture will be very brief. And primarily I'll be talking about ductile fracture for the most part, and this applies to the components of interest, which are typically zirconium alloys and austenitic alloys. The focus is going to be on properties in the reactor core, so I'm going to discuss the hardening mechanisms, that apply both mechanically strain hardening, but also radiation hardening, and precipitate hardening. And then I'm going to finish this first set of slides by talking about anisotropy. So there's this applies basically to zirconium alloys, and for those of you interested and knowledgeable of zirconium alloys, I hope you will find it illuminating what I'll talk to you about that as far as zirconium alloys are concerned. Okay, so let's move on. So the subject, the topic of this talk is strain localization, and as it relates to cracking. So one of the most obvious locations for strain localization is a crack tip. And I'm assuming that most of you have some science background, so that you'll have been introduced to some material science and will have heard of things called cleavage fracture. So cleavage fracture is just like in dislocation slip. Dislocation slip is an easy way to break all the bonds in a material. Without expending too much energy. So you gradually work your way across a certain area of material, breaking one row of atomic bonds at a time. The same thing with cleavage fracture. Cleavage fracture, if you can maintain a very sharp crack, you only have to break the bonds along a line that the edge of the crack, and the crack can then advance just by breaking one set of bonds at a time, and that leads to basically brittle fracture, and that only occurs when the material is not prone to ductile deformation. Slip is very difficult, and the only way to basically break the material, break it apart, is to cause the decohesion of the atoms, so break the atomic bonds. And typically this requires very, very high stresses. Basically the substantial fraction of the elastic modulus, and we're talking tens of gigapascals in terms of a localized stress to basically decohere a material. So, but especially for nuclear reactors, one does not use brittle materials such as this in nuclear reactors. They're very rarely used. And the only time that one would come across kind of cleavage fracture would perhaps be in a body-centered cubic material and at very low temperatures. So although body-centered cubic materials are much more brittle, especially when irradiated, than austenitic alloys, I'm actually not going to talk about them today because they're generally not used in the reactor core because of the embrittlement, low temperature embrittlement. So the worry would be for those materials is that if you ever drop the temperature, shut down the reactor, and they were under some stress, they could still potentially break because they have lost their ability to absorb any energy. So, and that's why body-centered cubic materials, which are more prone to non-ductile brittle failure, that's why they're typically not used in reactor cores. Although I understand some Gen 4 reactors potentially will use some ferritic steels in the core, but only at high temperatures, obviously. So high temperature is not a problem, low temperature it is a problem. So that's enough of cleavage fracture, just to know what it is, and that we don't basically trouble ourselves with cleavage fracture when it comes to reactor materials, and especially not during operation in the reactor core. But we do deal with ductile materials, the ones that you'll commonly know are certainly in reactor operation are austenitic stainless steels and nickel alloys. And very important, obviously, zirconium alloys. They're used for the fuel cladding, and certainly in the CANDU reactors, in heavy water reactors that run on natural uranium, much of the core internals are made from zirconium alloys. So from that perspective, coming from a background where I've worked largely in the CANDU nuclear industry, I have quite a bit of experience with the problems related to zirconium alloy behavior, mechanical properties, and primarily radiation creep, which is another issue. Anyway, moving on, one of the ways in which a crack can advance is certainly in a ductile fashion is by emitting dislocations. You have to, just like dislocation slip is an easy way to separate or to deform a material, it's basically takes too much energy, too much force to simply pull atoms apart. One can do this much easier if one has dislocations. And in the case of cracks, if you already have a crack, so you'll notice I haven't gone into, well, how does the crack form? That's another issue, and that's where we get into slightly esoteric territory, because I think largely people have to make certain assumptions about why cracks form. Now, so cracks do form where you have incompatibilities, where you have hard precipitates, or if you have stringers, material which doesn't bond very well, it doesn't dissolve or bond very well with the metal. So you can have parts of the material where you have some separation to begin with, and once you have separation, either because the separation can occur at an inhomogeneity, and that can happen either because you have a hard precipitate and it doesn't deform the same as the matrix, and eventually the stresses build up, incompatibility stresses build up, and you get some stress sufficiently high at a small enough scale that you can get this, in essence, the separation, the cleavage that on a microscopic scale happening and a crack being formed. The other way is for the precipitates themselves to fracture because they're under a lot of stress, because they're not deforming plastically, and that's another way to create cracks. But once you have a crack formed, it can grow, and the most well-known common method of growth is through dislocation emission, as shown in the slide here. And I should use a pointer, I guess. Yeah, as shown in the slide here. This slide just shows some typical fracture surfaces as well, and I'll be getting into that throughout this presentation, because there's basically two ways in which cracks can propagate through the material. One is in a transgranular manner. This can be ductile, cup and cone kind of failure, but it can also be in a brittle fashion or a semi-brittle fashion. And I'll be discussing that. And the other way for the cracks to propagate is along grain boundaries. Now, normally grain boundaries are the strongest part of any material, because it's very difficult for dislocations to glide in the complex grain boundary structure. So they typically the matrix will often yield long before the grain boundary might fail. However, the grain boundaries are subject to other forms of weakening, and we'll discuss that during this presentation, the remainder of this presentation. So we have two forms of crack to worry about, or to consider primarily. One is transgranular and one is intragranular. Let's move on. As far as the transgranular mode of cracking is concerned, conventional wisdom has it that typically, if you have a crack to begin with and you have inclusions in the material, the crack will tend to propagate along a plane where the density of the inclusions is highest. And again, what's happening here is that you have some stress intensification close to a crack tip that can, especially when you have an inhomogeneity, which is the precipitate and the matrix, that can generate sufficiently high stresses to create this decohesion, although I'm not sure. Perhaps there are models, I don't know whether there's any molecular dynamics models of separation of interfaces, but it is observed that you get this kind of micro void formation at precipitates, and eventually they will coalesce and allow for crack propagation. If the precipitates are not aligned in any high density plane, as they might if they were on a grain boundary, for example, you tend to get, my understanding, I'm just repeating what I've heard, you tend to get fracture which is more in a kind of a jagged form, and where the shearing at the edge of the crack happens in certain directions preferentially. So if you had a uniform array of precipitates, you might expect more of this kind of jagged cracking. I guess the crack progresses because this is the highest resolved shear stress in this direction, 45 degrees. Let's say I don't have the tensile axis here, but if the tensile axis was vertical, and then you'll probably get some hardening, and then you get to some barrier here, and then the crack can progress further at another 45 degree angle and basically move through the material like that. Who knows what the actual what's actually going on, and typically the type of failures is subject to the stress state and the degree to which the material is constrained. So what you tend to get, if it's a thick specimen, let's say it's a tensile specimen, you tend to get actually preferential failure at 45 degrees, which would basically is known as the plane stress condition, and but in the center you got constraints, and it's under what's known as plane strain deformation. I'm not going to go into that, but basically there's two ways in which a tensile specimen would fail, and it's all subject to the stresses and the constraints, the local constraints around the material. Just to summarize, we have this mechanism, typically how a material might form a crack, even without a crack, to create a stress intensity if the material is hardened and the stresses have built up sufficiently and the plastic deformation is sufficiently high that there is a large incompatibility between the matrix and the precipitates. You could get into conditions where you simply get decoherence and a microvoid formation, and even without the presence of a crack. And typically, in a transcounter fracture, it can either occur via this kind of mechanism, or it can occur by cleavage. And as I said, we're not going to talk about cleavage because it doesn't really apply to the conditions we're interested in. And then the other mechanism of interest is this intergranular fracture. And typically, this applies when the grain boundary is weakened, either by chemical attack, oxidation, or segregation. In this particular case, I'm thinking about helium bubbles, and that becomes very important when it comes to reactor materials. So again, we're still in the introduction mode, and so I'm going to talk about strain hardening. Just to get this out of the way, what is strain hardening? And this is basically when a material deforms, initially the matrix will be could be free of defects if it's an annealed material, but the deformation itself creates defects which then hinder the formation and the progression of additional defects. And what you end up with is a situation where the material, it gets harder and harder for the material to deform for a given stress. This is illustrated here. Many of you are probably very familiar with this. I apologize for going through some of the simpler mechanical engineering or metallurgy 101 type materials, but I just for the sake of completeness, I just want to put these down there so at least we understand each other and you understand what are the conditions I'm thinking about when I go on further to irradiated materials. For an unirradiated materials, there are certain things that are well known. If you have a tensile specimen and you put it in a load frame and you extend it, there's a region of deformation which is reasonably well characterized, and that's the period of uniform elongation. This is when the gauge section of the material tends to change. The material, the specimen elongates, especially in this thinner area, but it does so in a uniform manner, so that over this whole length of the gauge section we get a gradual, a uniform decrease in the dimensions. So by thinning the sample, the stress builds up, but at the same time it's work hardening because you're creating dislocation tangles, and at some point the stress is sufficiently high, but the hardening is sufficiently high that or actually before that, at one point, at a certain point, there will be a point where somewhere along this gauge length you will get some additional necking, and then it becomes a lot easier, some localized necking, and then it becomes a lot easier to deform, and you get a much larger strain for less stress, and the material then gets essentially, it's not that it's becoming softened, it's just that the region where the deformation is occurring is a smaller and smaller volume, and eventually it'll fracture. So this instability point could be because of the slight variations in the thickness of the machined tensile specimen, and that's typically what it is, but it could also occur if you have some inhomogeneities in there, some inclusions, some precipitates at a certain part of the material, and if you get some void and microvoid coalescence at that point, then you will get some preferential localized deformation there. So, so mostly when we're talking about tests and data from materials, they're often given in terms of the engineering stress, and the engineering stress is simply the stress that you applied, but based on the original dimensions. It doesn't take into account that the material here is getting thinner. So under this uniform elongation region, it's then possible to calculate what the true stress, because it's uniformly thinning, and then one can deduce basically from the elongation, from the length of the gauge section, one can deduce what the strain is, and from that deduce how the stress intensifies as we elongate the specimen. And this is the value called the true stress. So the true stress in the material can be calculated up to this point. Once necking starts to occur, it becomes much more difficult, and typically in tensile specimens, nobody tries to calculate the true stress once this more severe necking is concerned. So all along, the material is, because the gauge is elongating, because of constant volume, it has to be thinning at the same time. And if you look at an engineering stress strain curve, it would look like this, and the true stress curve looks like this. And you know, the point here where you would stop measuring the true stress would correspond to this, the ultimate tensile stress, something Björn, Zach Björn describes as the point of instability. Okay, so here's again a little bit more of the same. Different ways in which materials can be deforming in a tensile test. If it's a single crystal, you can excite slip on single planes, we get this shearing. If shearing can happen on multiple planes, especially if you have if you have the tensile axis along a specific crystallographic direction. So again, in this particular instance, the deformation, the thinning comes about purely by shear, and it's ultimately purely ductile failure until eventually the material can't get so thin that it can't maintain the atom simply part at that point. You know, on a microscopic scale, you will get some eventually decoherence. In a polycrystalline sample, or in a material with a lot of impurities and precipitates in it, it's not quite so pure, simple as this upper case here, and you tend to get this void and microvoid coalescence within the tensile specimen up until you get the failure. And again, a typical thing that happens in many thick specimens, thick now, is at the edges you get into a condition of plane stress, and at that point, and what I mean by that is the stress component perpendicular to the surface of the specimen is zero. So there's only stress within the plane of the material. Under those conditions, you tend to get more shear. So here's some dislocation dynamics simulation just to show what happens when you deform something and what forest hardening is about. Basically, I start out with a relatively low dislocation density. Let's say if it's already core worked, then you apply different degrees of strain, 3%, 0.3%, 0.8%, and this just illustrates what's happening when you do that. And the higher the density of the dislocations you get, the more tangled they are, and the harder it is to continue the the deformation. This is what's called the strain hardening. Zirconium alloys are peculiar compared to austenitic alloys, although I guess I could go back to basics and the crystallography and everything else, but I have to assume that you understand and know something about the crystal structures of different materials. And probably most of you are familiar with zirconium alloys in particular, and you'll know that they're hexagonal close packed, and you'll also know that the dislocation structure in zirconium alloys is a mixture of A and C types. So that's 1/3 1,1 bar 2O or 1/3 1,1 bar 2,3. And in the austenitic alloys, I'll talk about dislocations later, but in the austenitic alloys, there's only one type of dislocation, that's glissile, and that's the half 110 type dislocation, which is simply the shortest distance, interatomic distance of the atomic lattice. But in hexagonals, there are some peculiarities, and you can get this mixture of dislocations. Now, when it comes to hardening, it's much more interesting when it comes to the case of hexagonal zirconium alloys, in that you have this option or possibility. Well, actually, it's not even a possibility. It happens, and it is the reason why we see these complex network structures that typically one sees. And there's just one slide just to illustrate one example of how two dislocations gliding on two different planes with two different Burgers vectors, in this case a C plus A2, I think that is, and an A2 Burgers vector, if they cross one another, they can form an attractive junction. And what that means is that the energy of the combined energy here is lower than the self energy of the dislocations before they've interacted. So in forming this junction, the overall strain energy in the lattice can be lowered. And basically the two dislocations zip up. You know, it's just like a zip. So you can zip them one way if you apply a stress in one direction, and you can unzip them if you apply the stress in the other direction. But this network, when there's a sufficiently high density, also serves to harden the material. Carrying on still a little bit further with zirconium alloys, I mentioned there's two types of dislocations. I also mentioned I worked in the Canadian nuclear industry. So for that, we deal with zircon-niobium tubing a lot, whether it's pressure tubes or calendery tubes. And the texture of the tubing, pressure tubing in particular, tends to be like this, where you have, for the hexagonal crystal structure of the unit cell, you tend to have a lot of basal poles aligned in the hoop direction of the tube. And what that means is that if you deform the material, and I've taken a simple case here, let's say we cut two tensile specimens out. In this case, these are bent beam stress relaxation specimens, but it's same as tensile. Basically, if you take this transverse specimen and you pull it, in which case what we're talking about is pulling along the C-axis, you tend to get a lot of the C plus A dislocations that I showed you earlier. And again, the next slide I'll show you what this means in terms of the crystal structure. However, if you take a direction which is perpendicular to the C-axis, along the length, the longitudinal axis of the tube, and you pull it in this direction, you don't excite slip on the necessary planes to produce these C component dislocations. And what you see is for the one type of dislocation, you basically don't have any. You only produce one, the A type dislocations. What do I mean by that? So here's a schematic showing the hexagonal unit cell. What I've been talking about, and I apologize that I'm kind of coming at this in reverse, but when you pull a crystal of zirconium in the C-axis, you will excite slip on these planes. This is the pyramidal 1/1 plane, and the direction of the slip is C plus A, or some combination of C and A lattice vectors, where the A axes are defined as shown here. And again, I'm not going to get into Miller-Bravais notation and stuff like this, because I'm assuming some of you or many of you will be aware of it, but just to know that there is this way of indexing the crystal structure. And all you really need to know is that you pull it on the, if you apply a tensile stress or a compressive stress along the C-axis, you tend to get slip on these pyramidal planes. And if you pull a specimen or compress a specimen along one of these A-axis, you tend to get slip on this plane, the primary prism 1 plane. So these are the two main planes. Ignore that one for now. Yeah, just ignore it anyway. It's this one, which is a reasonably close packed plane, and this one. I've also marked the basal plane, which is typically the most close packed plane for materials like magnesium and zinc and what have you. That comes into play perhaps when you've got an irradiated material, but typically the CRSS for slip on 001 is generally higher than it is for the slip on 1/10. And if you're pulling along the A-axis, you're more likely to get deformation, slip occurring, because your resolved shear stress is higher, and the critical resolved shear stress that you need to create dislocations, or not to move dislocations, not create them, but to move them, is high. Is lower for these planes. The critical resolved shear stress is lower for these planes than it is the prism 1 planes, as opposed to the basal plane. And when it comes to the pyramidal, that has a higher critical resolved shear stress, but if your applied stress is in a direction which is not conducive to slip on either basal or prism, then you'll get slip on these pyramidal planes. So unfortunately, I'm recording this, so I can't go back, and so I would have, if during a presentation, I would have flipped back to the previous example, showing you the dislocations, the C plus A type and the A type. And for comparison, we have the austenitic structure, which is face-centered cubic, and I stole this off the internet. This is a depiction of the atomic arrangement for an austenitic stainless steel, and the plane of interest is this one that goes from each of the three corners of the cube like this, and this is the most close packed plane. I have some, during the live presentation, I'll have some ball models to show people how slip occurs in both the hexagonal case and the FCC, the cubic case. Suffice to say, when slip occurs in the cubic, it does so on these types of planes, and it does by two partial movements. It's easier to move this atom to there first and then to there, and then you get a half 110 displacement. And just so that you're aware, twinning occurs on successive planes. Twinning occurs in both the FCC and in the HCP metals. And I'll maybe talk a little bit about both later on. But in the HCP case, twinning can only occur on planes other than the basal plane. So the basal plane in the HCP is equivalent to this plane. It's the most, if you like, it's the most close packed plane for ideal packing, for ideal packing of spheres, which is close to magnesium. But in zirconium, because zirconium has a particular C/A ratio, you tend to get, because in zirconium these planes are the most close packed. These are the prism 1 planes. These are the ones where you'll get slip occurring. In the case of the austenitics, I mentioned the twin operation, as you may or may not know, and again I can demonstrate this with some ball models later, or certainly during the presentation, but I'm also going to be attaching some YouTube links to demonstrate what's going on with a ball model with twinning. But basically you've got slip on 3 planes. Twinning is a bulk shear, and what happens is that for a single twin operation, for example, a unit twin operation, you have this is a partial, the first partial on one plane, and when you see it in the ball model, this atom can only go that far because it bumps into another atom, so it can't go any further. But the atom on the plane above can move in the same direction, and then the atom on the plane above that can move in the same direction. So over the space of 3 layers of atoms, close packed atoms, you can get a deformation or a shear deformation, which amounts to this vector. And again, that's much easier to demonstrate with a ball model rather than try to illustrate it. And I have some YouTube links embedded in this presentation that I'll show you later. So we're still in the introduction mode. I'm not getting into the main part yet. Just simply discussing some of the basic mechanisms of deformation and hardening. Just brief examples. So you probably heard about precipitation hardening. Now, for those of you who are familiar with zirconium alloys, you will know that zircaloys, for instance, contain precipitates, but they're generally not added for mechanical properties. The precipitates in zirconium alloys are added for corrosion behavior or hydrogen ingress. So in zirconium alloys, a lot of their hardening comes from solution hardening. So it's just basically the addition of tin or the addition of niobium raises the friction stress in the lattice, and therefore raises the yield strength accordingly by solution hardening. Dual phase alloys, niobium dual phase alloys, they do tend to have they're harder still, stronger, not necessarily, stronger and harder, so a little bit less ductile than zircaloys, but a lot of that essentially comes from the grain refinement. So the dual phase nature in a zirconium alloy, for instance, allows for smaller grains. Allows one to retain smaller grains in the as fabricated product. And a lot of the increase in the strength comes from the effect of the second phase on refinement. But in austenitic alloys, precipitates are used extensively for modifying the properties of the material. So this slide just shows some of the types of elements that one would add to different alloys, whether it be a stainless steel or nickel alloys. Nickel alloys are the ones I'm most familiar with. And nickel alloys in particular, they have a interesting precipitate, which is an ordered gamma prime precipitate, and this is used extensively to harden the material. And that's why basically nickel alloys which are hardenable by the formation of gamma prime, that elevates the yield strength very substantially, and that's why these materials are very good for springs. So although their ductility may be reduced somewhat, their yield strength is elevated substantially through the inclusion of the gamma prime precipitates, and yeah, they're then difficult to deform, but are also very good then spring material. So there are different types of these ordered phases, and one can produce the right size and number density by appropriate heat treatment. Typical heat treatment for austenitics is 700 degrees C for like 10 hours, something like that, to create the gamma prime precipitates. But this section of the periodic table is also just gives you an idea of some of the other elements that one is dealing with when it comes to either solution or precipitation hardening in nickel alloys and austenitic stainless steels. The gamma prime phase are identified here. These are all the elements which are soluble in the gamma phase. So in the gamma phase, which is basically the austenitic phase, which is created by the nickel, by the addition of nickel. So even in a stainless steel, there's sufficiently high nickel that the material is primarily austenitic, although there is some ferritic typically. Another type of precipitate which is important is the carbides. They tend to form like borides at grain boundaries, and this is important when it comes to the reaction with alloying elements, in particular chrome. So if you have chrome added to your alloy for good corrosion properties, but your heat treatment schedule is such that you deplete the chrome because it forms carbides close to the grain boundary, you'll get a depletion of chrome, and that's not good news, because then you're inviting intergranular attack or heightened oxidation, particularly along the boundaries. It's localized at that point. So typically one adds, or the suppliers of different materials might add other elements, titanium, niobium. I'm not sure they add hafnium, but there's an interesting story about hafnium I'll tell you later. And these are all carbide formers, and when they will compete with chrome and either minimize the amount of chrome that's depleted or actually completely eliminate any of the chrome depletion, simply because they preferentially then soak up all of the carbon. So the way that precipitates affect the mechanical properties, they're basically barriers to dislocation slip. So dislocations will glide through the material. If the precipitate is small, they can cut through it, but it still takes some effort, takes some force to pass a dislocation through a precipitate. And once the precipitates get large enough, it's really when the spacing between the dislocations becomes large enough through aging. But typically aging both increases the spacing between precipitates, but also increases the size of the precipitates. So by and large, it's actually a combination of the two. And but enough be it said that with longer aging times, as you grow precipitates, as the spacing becomes larger, then R01 looping becomes the primary form by which dislocation will pass through a field of precipitates. So, and in that case, when the precipitates are small, there's a high density, you get some hardening, and then at some point, when in this case, this is the size of the precipitates. Once they get past a certain size, and the spacing becomes larger, R01 looping becomes more prevalent, and it's easier then for the dislocations to pass through a field of precipitate. There are different formulas for describing how hardening, how precipitates harden the material. There's this alpha, the dimensional strength factor, which is typically studied by many different material people. So you have both the geometric effect, but also the nature of the precipitate itself. But that can be its size, the size of the precipitate, as well as the spacing. So the spacing is given by this value L, and that's also important. Given a certain size, the size factor may come into play when it comes to this dimensional strength factor alpha, but it also comes into play simply because of the role it has on the spacing of the both within the slip plane, the interprecipitate spacing, but also the spacing of the precipitates between different slip planes. So how is this utilized? Or when it comes to, let's pick an alloy like Inconel 718. In a solution annealed condition, let's say it's been heat treated at 1,000 degrees centigrade, something like above that, to dissolve and at that point, any of the gamma prime would be completely in solution. And this is the effect of irradiation on the solution annealed material, and what it illustrates here is that in very low doses we have a typical stress strain curve, lots of ductility, some hardening, but as you irradiate, as you increase the dose and you create radiation damage, you get to a much more embrittling effect. Whereas in a precipitation hardened material, it's already strong anyway, so the radiation doesn't really add too much. But what radiation does do is reduce the ductility, because you're adding to the number of barriers, which are not really increasing the strength, but certainly reducing the ductility. One other thing that you see in Inconel 718 is with increasing doses, if you go to very high doses, the doses we just described there were down about 1 dPa, but once you've gone past a certain low dose, what you see eventually is the material gets softer. And the reason it gets softer is because the precipitates are actually dissolving with the irradiation. Another thing which is common in Inconel material, especially high dose, 20 dPa in this particular case, is embrittlement. And you can get conditions where the ductility is basically gone. This particular instance, although it's not proven in this case, is probably linked to helium. So that embrittlement is shown here in terms of the fracture surface. This is Inconel 718. I put in 1500 APPM of helium, and I'm trying to think that may be an overestimate. I've got to check that number. So I will check that number. I thought it would maybe be more like lower than 1000 APPM. I have to check that. Anyway, irrespective, there is a lot of helium generated, even though this particular sample was irradiated with 800 MeV protons. The protons themselves at these energies also create helium, just as thermal neutrons, low energy neutrons, create helium. So why do we have this temperature difference? A dose dependence, you get the softening, but also the softening is more softening. You get more softening at lower temperatures. And the reason is, if we look at gamma prime and then we irradiate it, we come in and we're disturbing the lattice and we're dissolving these precipitates as we irradiate more. And in the case of this particular example now is Inconel X750 unirradiated, but then after irradiation at a certain temperature, if it's a high temperature, we still retain some of the gamma prime, but at lower temperatures we see less of it. So basically at the lower temperatures the irradiation dissolution is more extensive. Irradiation dissolves and dissolves or disperses the gamma prime, and but at a higher temperature you can get some reprecipitation, and the disordering is less pronounced. So you get this gradual decrease because you're dispersing these precipitates, but there's a temperature dependence, there's a difference. It's more prevalent at low temperatures, which kind of is a little bit counterintuitive, but it's precipitation hardened materials. I mentioned the case of Inconel 718, but also this is X750. That was the last example, in fact, and this just shows hardness as a function of dose for two temperatures. I'll call it hot and not hot in this particular case, and the same kind of results you got with the 718. Basically, there's more softening at a lower temperature. So after an initial transient, there is a gradual decrease in hardness. Here's a piece of work by Tan and Busby where they've characterized the alpha parameter. The matrix strengthening factor. I should have put this on the slide, that this was the alpha parameter. I mentioned there was like a quality factor for the precipitates. Certain precipitates are much more resistant to the passage of dislocations than others. And they studied this in one particular example, and what they showed is that surprisingly cavities are quite strong barriers for dislocation slip. This is important. There are many different things that are going on when a material is being irradiated. You're getting interstitial loops created, you're getting disordering of the gamma prime, you're getting cavities formed, you get small precipitates formed, and you're also getting dissolution of the gamma prime. But what largely happens is the material softens, and that's largely because of the dissolution of the gamma prime.